So you can see noise in communication system, signal to noise ratio, then leave this band pass structures, noise in linear receivers, noise in AM receivers, noise in SSB receivers, and noise in frequency modulation. Okay. So your topic is noise in. So how we will calculate the noise in a communication system? Okay. First of all, we have to see the introduction. Then we will move to the derivation. I'll tell one derivation today, a small derivation. Then you can proceed with other derivations. All will be in the same pattern. Okay. So coming to first, we have to assume some concepts. Now, what is this concept? Assuming concept means what? So noise always is a random signal. Okay. So we can't expect noise. So when you are watching a movie, okay, so you'll be having the picture perfectly clear and sound also in the Dolby and all. The sound will be perfectly all right. But when the audience shouts, okay, when the audience in the theater, when the audience, if they shout continuously, you may not be able to listen to the picture sound. Okay, you picture anyway will be visible, but audio will not be that much clarity. Audio can't be listened. Why? Because of the nuisance created by the audience, unnecessary whistles, unnecessary all unwanted things they'll be doing, right? So when that happens, you cannot listen to the original sound of the picture. Okay. So noise is considered as a random signal. That is random. So whatever the noise that is created in the theater is random in nature. You cannot determine that noise also. So how much time it will stay, how much amount it will be there, that like that. In signals and systems terminology also, the noise is random in nature and it cannot be predicted or it cannot be determined. Okay. So we will make some concepts so that the noise is reduced. Okay, we can't eliminate noise, but we can reduce the noise. Okay, so what are the assumptions that we are taking? I have written here. First assumption is the mean of the random process. So noise is a random process. Okay, noise is considered as a random signal, and that particular process we say it as a random process. Okay, so for random process, first one, if you see the mean of random process. So what we are assuming is both the noise and signal are generally assumed to have zero mean. Okay, so when we want to calculate the mean of the random process, it is assumed to have zero mean, both the noise as well as the signal. Okay, then second one is autocorrelation of the random process. So what is this autocorrelation? You might have studied about this autocorrelation function, then power spectral density, PSD, all this you might have studied in your random signals. Okay, the same I am repeating here. Okay, so with the white noise, generally, even though any noise is there, we can assume white noise is always there. It is completely distributed throughout the spectrum, right? It is distributed throughout the spectrum. So you know this, right? This is frequency. So throughout the frequency spectrum, the power spectral density is distributed. The noise power spectral density is distributed, and it is generally given by N0 by 2. Okay. So that N0 by 2 is written here, and dou of tau is the delta function, right? So autocorrelation of random function is represented by RW of tau, which is equal to N0 by 2 into dou tau. Okay, this is the delta function, and this is the power spectral density of white noise. Okay. Then the third point is the spectrum of random process. Now, what is the spectrum of random process? It is this one. The spectrum of random process is represented like this in frequency domain, and its value is N0 by 2. So what is this SW of F? It is nothing but it is the power spectral density of white noise. So autocorrelation of white noise is RW of tau, and white noise power spectral density is SW of F, and its value is N0 by 2. Now, if we want to compute the noise power, then we must measure the noise over a specified bandwidth. So that specified bandwidth is B of t. So in this case, if you see minus infinity to plus infinity, okay, if we want to calculate the noise bandwidth, then we have to take only certain portion, okay. So that is represented as BT. Equivalent noise bandwidth is BT. So the average noise power is represented as N, and it is equal to N0 into BT. So what is this N0? This one, the power spectral density of white noise in two sides, okay, positive as well as negative. That's why it is divided by 2. So N0 into BT is the average noise power. So this is, remember this equation, we will use later. So these are the assumptions we have taken. Now what happens is when the signal is transmitted, okay, at the receiver only we will be talking. Why? Because the noise is added in the channel, right? So noise is added only in the channel. At the transmitter side, if the signal is having noise, we will not transmit that signal. If it is with noise, we won't transmit that signal. Simply we will cancel and we will use another signal for transmission. But after transmitting the signal is having noise. The noise is added. Okay. So at the receiver only we can see about the noise. At the receiver only we can talk about the noise. Okay. So this is a receiver. Some receiver. Assume some receiver. So S of t is the transmitted modulated signal. Okay. This is the transmitted modulated signal. So in the channel, what happens? Some noise will be added. Okay. So S of t is the signal that is being transmitted, and there is an adder here. So in the receiver, initial stage of the receiver will have white noise, even though the receiver is perfectly designed, white noise or Johnson noise is always available. Okay. So that white noise is represented with W of t. It is added to the signal. Okay. So this is the signal which is having center frequency FC. It is received at the receiver. Okay. So whether you take AM, FM, DSBSC, SSB, for all the signals, the center frequency is carrier frequency FC only, right? So center frequency is FC, and this is our received signal spectrum. Okay. Now this signal is added with the white noise in the receiver initial stages. Now white noise is added. So you can see a straight line here. So I told you white noise spectrum is this one. So you can see a straight line here. So this is the white noise plus signal. So that is represented as R of t. So R of t you can see here. R of t is S of t plus W of t. Now this signal is passed through a band pass filter. So here this band pass filter will allow a band of frequencies like this. Okay, it allows only a band of frequencies. And here to the R of t, whatever the white noise that is there, that will be transformed as N of t. Means whatever the noise that is there with the signal, that noise and this white noise, all that is combinedly we call it as narrowband noise N of t. Okay. So finally the band pass output is X of t. So X of t is equal to S of t, means this signal plus W of t, right? So the W of t after passing through the band pass filter is transformed as N of t. Okay. So X of t becomes S of t. This is the signal term and this is the noise term. Okay. We have two terms now. Previously we have taken only the signal and we have how it is recovered at the receiver we have seen. But we are adding noise also. So if noise is there, what will be the performance of the system? We are going to see. Okay. So X of t is S of t plus N of t. So in this process, what we are going to do is we are going to calculate the signal to noise ratio. One minute. So from here on, what we are going to do is we are going to calculate the figure of merit. So noise performance. So noise performance is given by figure of merit. All of you write in your notebooks. Noise performance is given by figure of merit. Figure of merit. So students' performance, how it will be given? Through the exams. So we can, through the exams, we can say, okay, the student got 9 out of 9 or 10 out of 10 CGPA. So he is a very good student. If he gets or if he fails in a subject, we say he is an average, below average student. If he passed with minimum CGPA, we say he is an average student. If his CGPA is high, we say he is above average student. If he gets 10 out of 10, we say he is outstanding student. Okay. In that way, student performance is calculated through his marks, through his performance. Similarly, noise performance is calculated by figure of merit. Okay. So figure of merit has to be calculated. I told you 4 derivations will be there, right? So the derivation final output is figure of merit. So figure of merit formula for any modulated systems, AM, FM, for any system, okay, is SNR post detection to SNR reference. So this is the formula to calculate FOM, figure of merit. So SNR post detection means in the receiver will receive the signal, noise will be added to the signal, then it will be demodulated. Okay. So demodulator or detector will be used after, if you take a super heterodyne receiver, what happens? RF amplifier, mixer, local oscillator, then IF amplifier, then detector. Okay. Right. So this is the general process for a super heterodyne receiver. So before this detection part, whatever we calculate for this receiver, that is SNR reference or pre-detection. SNR pre-detection means before detection, pre-detection. After this detection, low pass filter, amplifier, finally output. Okay. So this, whatever the SNR calculated at this is called as post detection. So post detection means after the detection process. Pre-detection means before the detection process. Okay, before the detection process, we calculate SNR, that is pre-detection. Pre-detection is converted as SNR reference. So the formula for FOM, figure of merit, is SNR post-detection by SNR reference. This is the formula. Okay, so this is what we are going to calculate. Okay, so this is what is calculated. You can see a system here, general system. So modulated signal S of t. Initially white noise is added. White noise, W of t. S of t plus W of t is R of t. R of t is passed through the band pass filter. So band pass filter is X of t. X of t is S of t plus N of t. Now this X of t is passed through the demodulator. Okay. So after demodulation, you will get the message signal X of t. Okay. ఇక్కడ X of t ని మనం మెసేజ్ కాదమ్మా. X of t here is our output of band pass filter. Okay. So this output is now given to the demodulator, and demodulator output is our message signal. It is represented as M of t. Okay. So first of all, we need to calculate the signal to noise ratio. So for this, how we will calculate the signal to noise ratio means E means expectation function. E of S square of t by E of n square of t. What is signal to noise ratio? Signal power by noise power, right? So signal power by noise power. So signal power is calculated as noise power. So signal power by noise power. Signal power is calculated as expectation of S square of t. Noise power is expectation of n square of t. Okay. In this way, we will calculate the SNR. So if the signal to noise ratio is measured at the front end of the receiver, then if we measure signal to noise ratio at the front end, means pre-detection, what it will give a measure of the quality of the transmission link. Means how good the quality of the transmission link is there, means that how that signal will be transmitted through a transmission link, fiber core. Maybe it is a fiber, okay, coaxial cable, or some waveguide through which the signal will be transmitted. So the quality of the transmission link is very good if signal to noise ratio is high. If it is low, the noise level is very high. Like that we will say. So SNR measured at the front end pre-detection will give the measure of the quality of transmission link and receiver front end. Then the signal to noise ratio measured at the output of the receiver is, it gives the quality of the recovered message signal. Information bearing signal means message signal, whether it is audio, video, or picture, sound, whatever it may be, it gives the quality of the recovered message signal. And finally, the reference model is equivalent to transmitting the message at baseband. The same diagram, this same diagram has been reduced into two parts. So message signal with the same power as the modulated wave, the channel noise is added, and finally the low pass filter having bandwidth W. So previously we used to represent FM. Now that FM bandwidth is represented with the W. Okay, in this particular noise chapter. So SNR references average power of the modulated wave to average noise power. And figure of merit, I gave you the formula post-detection SNR by reference SNR. Okay. So if we get the high value of figure of merit, then the noise performance is better. We can say the noise performance of the receiver is good. It is better. Like that we can say, provided figure of merit is high. Now, whatever we have seen is the pre-detection SNR can be calculated before the detection process, and post-detection is calculated after the detection process. And the reference SNR is based on the transmission model. I told you, I will tell again, okay, when we are calculating. And finally, the figure of merit will be calculated. Okay. This topic is not there for us. Now, only this topic is there. Okay. So here, students, please remember whatever is there as M of t. M of t is the message. This is a new textbook, Simon Heiken textbook's notation. So we have written like this. So AC M of t. Amma time ayipinda. Students, can you wait for another 5 minutes? I'll just give a glance of this topic and I will close. 5 minutes, another 5 minutes.
Okay, ma'am.
Okay. So if we want to calculate the figure of merit for DSBSC, first technique. Okay. So first what we have to do is we have to calculate the SNR, pre-detection, post-detection, and reference SNR. Then we have to substitute that value in the figure of merit and we will get the value. And if that value is more, we say the quality of receiver is very good. If the value is less, we say it is not good. Okay, like that. Now, how to calculate the figure of merit? How to calculate the SNR? So, initially, assume S of t. We know S of t for DSBSC is X of t into C of t. That is our notation, right? X of t means AM cos omega mt. and C of t is AC cos omega Ct. Now here this theta is also considered omega Ct plus theta. Theta is the small carrier phase. So it will always be there in the DSBSC. Okay, since we are calculating noise, every small part will be adding for the noise. So we are assuming this part. Okay, actually it is x of t into C of t. DSBSC is x of t into C of t only. The equation is x of t into C of t only. Here our x of t is m of t. Okay, to C of t. So x of t into C of t. So AC x of t cos omega Ct. C of t means cos omega Ct. Plus a small theta is considered, which is the carrier phase. Okay. Now leave this equation. This is the basic DSBSC equation. Now coming to the picture. This is the DSBSC receiver using coherent detection or demodulation. So up to this point, this part is detection process. And this is pre-detection. Okay, this is pre-detection. And this is post-detection. Okay, so for pre-detection SNR, we need to calculate signal power, noise power. For post-detection SNR also, we need to calculate signal power, noise power. Okay, by using this particular diagram. So in DSBSC, receiver, in any receiver, RF signal will be given to a mixer, a local oscillator, and IF filter is our band pass filter. And finally, from the IF filter, the output is given to the detector. Okay. So in this process, initially RF signal means our DSBSC signal. So that signal is represented as FRF. Okay. So here you can see FRF is the input to the mixer. Now mixer will be, here you are multiplying the locally generated carrier signal with this. And now it will generate intermediate frequency that is passed through the band pass filter. Here band pass filter means intermediate frequency filter only. Okay. So when this input is passed through the band pass filter, you will get an output x of t. So that is written here. X of t is S of t plus S of t. X of t is S of t plus N of t. Okay. So S of t is signal power and N of t is noise power. Okay. So first we will calculate the signal power for S of t. So the signal power S of t should be calculated and we should know the DSBSC equation. So DSBSC equation is AC cos 2 pi FCT plus theta into e power m square t. Okay. So it comes to AC square P by 2. Okay. I will show all this. Okay. I will write. So AC square P by 2 is the signal power. Then comes noise power. So noise power in the assumptions I told you N naught into W. W is the bandwidth. Here the band pass filter is having a noise bandwidth of BT. So N naught into BT is the noise power. So signal power by noise power is SNR. So signal power is AC square P by 2 into this N naught into BT. So this is our signal power. SNR pre-detection. Then SNR reference. SNR reference can be calculated from the pre-detection as AC square P by 2 N naught, and bandwidth is generally represented with W. That is the only difference. Okay. So this is the SNR pre-reference. Now we need to calculate post-detection SNR. So to calculate post-detection SNR, the signal is passed through the demodulator, low pass filter and all. So x of t is S of t plus N of t. N of t is represented as Ni of t cos 2 pi fct means cos omega ct minus Nq of t into sin 2 pi fct. So this is the N of t value. Narrow band noise is given like this. Okay. So here Ni of t and Nq of t are the in phase and quadrature phase components of N of t. So mixer 2 output is V of t, which is x of t into cos omega ct. So we have multiplied and we will get this equation. So in this equation, this part is the signal and this part is the noise. So we have to calculate signal power and noise power. So signal power for this is half AC square into P and noise power is half Ni into T. So noise power will be 2 N0 W. So post detection SNR is AC square P by 2 N0 into W. So finally figure of merit is post detection SNR by reference SNR. So if you substitute these two values, you will get a 1. So after substitution, the value is 1. So we consider the figure of merit 1 means it is a high value. Okay. So it is a high value means it indicates the quality of DSBSC receiver is fine. It is good like that. Okay, students. So mixer 1, a carrier signal, RF signal, output is passed through band pass filter. Then output is given to mixer 2, carrier cos omega Ct. This is X of t. And this is output is given to low pass filter. And finally, the output is message signal or modulating signal. Okay. So DSBSC signal is represented as AC cos omega Ct into X of t. Right. So theta is a small value considered initially, but later on we will presume that it is not there. So DSBSC signal is represented as C of t, means AC cos omega Ct into X of t. Okay. Now SNR pre-detection. Pre-detection means up to this point you need to calculate. Post-detection means this is post-detection. This is post-detection. And this is pre-detection. Why this is post-detection means this is detector. So before the detector, whatever the process that is taking place is pre-detection. Okay. So SNR pre-detection means the formula is, what is the formula? You have to calculate signal power by noise power. So signal power. So here before post detection, the output is this value. Okay. So up to this point we have to see. So what is this? S of t plus N of t is X of t. Right. So S of t, what is S of t? We need to calculate AC cos omega Ct into X of t. Okay. So this is the DSBSC signal S of t. Okay. So we need, how we can calculate the signal power? I told you E of expectation of S square t. So expectation of S square t, how we will write? Expectation of S square t means, what is the signal? Expectation of AC cos omega Ct into X of t whole square. Okay. So we can divide, these two are individual signals. So we can divide expectation of AC cos omega Ct whole square into expectation of X square t. So these two are individual signals, C of t and X of t. So we have separated. Okay. Now expectation of this value is P and expectation of this value, expectation of message signal is P. Maximum power, signal power, message signal power is P. Okay. Then what about this one? How to calculate this expectation of this value? We can calculate by taking the integral 1 by t minus t to t AC cos square theta is can be written as cos 2 theta means 2 omega ct plus 1 divided by 2 into dt. So AC, this value AC, whatever is there, square value, right? So AC square by 2 into T into this value. If you integrate it, you will get only 1. Okay. So 1 in the place of T minus T, you will get 2T. So this 2T, this 2T will be cancelled. So you will be getting AC square. I'm sorry, this becomes AC square. You will get AC square. Yes, AC square. Now, we need to calculate the signal power. So signal power is 1 minute. I had a small doubt. 1 minute. So here, if we integrate this cos 2 omega ct plus 1 by 2 already I took out. So what will be this value means 1. So in the interval t minus t. So if you do the calculation part, you will get only t, right? So the final answer for this is VC square, means AC square by 2. So 2 will be there. Okay, this t, this value is t. T gets cancelled and you will get AC square by 2. So signal power by noise power is SNR. Okay. So signal power is AC square P by 2. And still we need to calculate the noise power. So noise power N of T. So initially before this, whatever the noise that is there, it is given as N0 into BT. So for a small bandwidth, we can calculate the noise power as N0 into bandwidth. And the indaka chupichan kadama N0 into BT is the noise power. So we can substitute N0 into BT. Means it comes to AC square P by 2 N0 into BT. Okay. So this is the signal power. This is the SNR for pre-detection. Okay. So if we want to calculate SNR reference of DSBSC, it is AC square P by 2 N0 into W. In a similar way, we need to calculate for post-detection also. So in the post-detection, X of T is given to the detector and X of T is multiplied with cos omega Ct. So what is X of T? In our case, S of T plus N of T. So this into cos omega Ct. So narrowband noise N of T is represented as Ni of T into cos omega Ct minus Nq of T into sin omega Ct into, this is the Ni of T. So plus S of T into this value cos omega Ct. So to the mixer 2, we are giving cos omega Ct and X of T, right? X of T means S of T plus N of T. So this multiplication I am doing. So if you elaborate this, okay, whatever the output of this is V of T. So V of T is this value Ni of T into cos square theta means 1 plus cos 2 omega Ct by 2 minus Nq of T into this sin A cos A means sin 2A sin 4 omega C, 2 omega Ct or 4 pi FCT by 2. Then plus S of T is AC cos omega Ct into X of T into this cos square. So it comes to cos square. So Ni of t by 2 into Ni of t by 2 into cos 2 omega ct minus Nq of t by 2 into sin 2 omega ct plus this comes to AC x of t into cos square means 1 plus cos 2 omega ct by 2. So whatever the signal that is left is AC x of t by 2 here. Then this one Ni of t by 2. So this will be the low pass filter output. V of t is passed through the low pass filter. So low pass filter will eliminate all the high frequency components. So whatever is left is only two terms. One is signal term and another one is noise term. Again for this, we will calculate the signal power and noise power. So signal power means expectation of S square T. So in our case, S square means it is AC square